Hello everybody! Today we're going to talk about conservation of energy equations. So, the equations we're going to talk about are going to be just basic equations on how to set up energy transformations from one step to the next. And we're only going to do these four types of energy. Potential energy, so when I lift something up in the air, it has potential energy, or if it's up in the air, if there's height to it, there's potential energy. Kinetic energy, so if it's moving, there's kinetic energy. Elastic energy, or energy of a spring, so if you stretch a string or a bungee or something, there's energy stored within that string. And then dissipated energy, which is the same thing as saying work done by friction. So let's go through some examples and talk about how do we set up these conservation of energy equations and how are they helpful. Let's go. All right, here I'm going to take a rubber band and I'm going to stretch it. Here's a rubber band launcher. I'm going to take this rubber band and I'm going to stretch it down. So right now I have elastic energy in the rubber band, and then I'm going to release it. Boom! So the elastic energy, it went to kinetic energy because when it left the launcher, it was moving, and then the kinetic energy went to potential energy. So, to write a conservation of energy equation, it looks like this. It started with elastic energy, ES. Then it went to kinetic energy, EK. Then it went to potential energy, EP. Then when it fell back down, it had kinetic energy again, EK. And then when it eventually hit the table, then all the energy got dissipated, ED. So, it started with elastic energy from the rubber band. The elastic energy converted to kinetic energy. The kinetic energy made it go up in the air, go into potential energy. Then it fell back down, so it went back to kinetic energy. Then it landed, hit the table, and stopped, so all the energy was dissipated. There's our conservation of energy equation that explains every single step along the way, where the energy started from and where the energy ended up with. And all of those are equal because according to the first law of energy, whatever energy you start with is the energy you get at the end. Now, if I wanted to solve some information for this problem, I would literally just use these equations and substitute the numbers in for these equations. So literally I could say, all right, elastic energy is 1/2 kx squared. Remember, k is the elastic constant, how strong the spring is, and x is how far do you stretch it from its natural position. And then x is squared. That equals the kinetic energy it left with, 1/2 mv squared, where m is the mass of the thing that's being launched, v is the velocity that it's traveling. That equals the potential energy, which is mgh, mass, acceleration of gravity, height. Then that's going to equal how fast it was going when it landed, 1/2 mv squared. And then finally, I can figure out the dissipated energy by frictional force times distance on the table. You can figure how much force was applied by the table to stop it. And also, another word for dissipated energy is work done by friction. Let's go through another example. All right, let's say I have this ball here. I have this ball, and I start with the ball in the air, and I drop it. Boom! If you notice, the ball doesn't bounce back to its original height. It starts with potential energy, I drop it, it goes to kinetic, then the kinetic goes to potential, but not as much potential. So, boom, boom, boom. Where's the other energy go? It has to go dissipated. So here's how you would write that conservation energy equation. The ball starts with potential energy, EP. Then it goes to kinetic, EK. Then it bounces up after it hits the ground to potential energy again, but some different amount of potential energy because some of it got dissipated. So I'll call it EP2, some different height, EP2. Where'd the other energy go? Dissipated. So I'll put ED. And then that would be for one bounce. I could do the same process for the second bounce. Now it starts with this much EP, and basically we're back here. It starts with like whatever EP I start with, it's going to bounce again, go to kinetic, and then some is going to be dissipated. We'll get to that in a second. So what I can do is I can do a little substitution here again. I have mgh equals 1/2 mv squared. So I can figure out like how fast to hit the ground with, and then I set that equal to mgh2 because it was a different height plus dissipated energy, or frictional force times distance. And I can figure out how much dissipated energy it has, how much potential energy it has, and its efficiency. If you remember, the equation for efficiency is this. Efficiency is your useful energy over your total energy. So let's apply that here. Let's say I started with 10 joules of potential energy. 10 joules of potential energy. Then it went to 10 joules of kinetic energy. Then, when it bounced up, it has both potential energy and dissipated energy, so maybe it was like 5 and 5. It doesn't have to be 5 and 5, it could be any value. It could be 7 and 3, it could be 8 and 2, it could be 4.5 and 5.5, as long as I add up to 10. But now if I want to find the efficiency of this ball, what I would do is I'd take my useful energy, which is everything that's not dissipated, so ignore the 5 joules of dissipated energy. The stuff that's not dissipated is 5, so my efficiency would be 5 divided by my total energy of 10, so that is 0.5, or 50% efficient. 50% of this ball's energy was useful, the other 50% was dissipated. And I can actually use this because now I can repeat the process. Let's say I do start with 10 joules of energy, and it bounced up to 5 joules of potential energy. That was useful. Now on the second bounce, now it has 5 joules of energy, and 50%, we just proved that it's going to be 50% of the energy is going to be dissipated. So if it has 5 joules of energy on the start of that second bounce, then after that second bounce, it's going to have 2.5 joules of energy. And then, so 50% of the energy is going to be lost every single step along the way. So in the first bounce, 50% of the energy is lost. Second bounce, 50% of that energy is lost. Third bounce, 50% of that energy is lost, etc. It's going to be half the bounce every single time because that's what the efficiency is telling us. It's telling us how much energy is lost each step of the way. Awesome. Let's go through another example. Here I have a spring car. And basically, it's just a car with a spring in it. I'm going to push the spring in and see what happens. So when I push the spring in, let it go, the car took off. So I'm going to show you that again. Newton's third law, right? Action, reaction. But now, how can we apply this to energy? Well, if you looked at the car again, the car started with elastic energy because there's a spring in the car. It's a spring on the car. So it starts with elastic energy, ES. Then the car went to kinetic energy because it was moving. Then the car stopped. It stopped moving because of friction. So all the kinetic energy went to dissipated energy, or work done by friction. That's the same thing. Work done by friction. So ED, or we can just call this work. And there you have it. If I knew any one of these energies, I can figure out all three. So essentially the way I can write it out is this. 1/2 kx squared. So if I knew the strength of the spring, or how far I push it in, or both of them, I can figure out the total energy. If equals 1/2 mv squared. So if I knew the mass of the car, or how fast it went, I can figure out the total energy. Or frictional force times distance. If I knew the frictional force on the car, and the distance to travel, I can figure out the total energy. All three of them are equal to each other. So once I find one, I also know all three. Very cool. Let's do another example. Here I have a ramp, and I have this weight here. It's a 1 kilogram weight. I'm going to take this spring scale and measure how much force does it take to move the weight up the ramp. So I'm going to drag it up the ramp here, and boom, drag it up the ramp. And I can measure that force, and now it's on top of the ramp. Boom. Now, if I were to take that same weight, instead of dragging it up the ramp, what if I started it down here, and I lifted it straight up? Put it on the ramp. The question is, which one was more work? Which one was more work? And the answer is, they're exactly the same because of that first law of energy. Energy can't be created or destroyed, it simply changes forms. So if you think about it, here's what the conservation of energy equation looks like. Okay, so here's my ramp, and what energy is not written down here is just work in general. Work is force times distance. Like dissipated energy is work done by friction, so it's frictional force times distance. But work in general is just any force times distance. So here's what happened. I took that weight. If I used the ramp, I applied a force on that weight, and I moved it up a distance up the ramp, whatever this distance was. When I ended such work, when it ended, this weight now has potential energy. It's on this ramp, it wants to fall, it has potential energy, and so, according to that first law of energy, my starting energy of work has to equal my ending energy of potential energy. So work equals EP. So to figure out what that energy is, what is EP? It's mgh. There you have it. This shows you that they're the same value. Force times distance. So when I apply force times this distance, it's the same amount of work, same amount of energy being used as if I take the mass times acceleration of gravity times the height, the potential energy. So the work done on an object, raising it up, is the same thing as the potential energy because they're equal energies. That's cool. So really, which was one work? They're the same. Which one was easier? Well, that one is going to be using the ramp because it gives you something called mechanical advantage. It increases the distance you have to travel, but reduces the force. Let's talk about levers. Levers do the same thing. If I have a lever, a first-class lever, so a first-class lever is when the fulcrum's in the middle. So I'm going to take a lever, and I put the fulcrum here, and I try to lift up a heavy object on this side, and I push down on this side, so I push down with some force on this side, it lifts up the object on this side. Well, according to the conservation of energy rule, I push down on this side, so I apply a force times a distance. But this arm, this lever arm, the applied effort arm is going to move a really, really, really big distance. And it's going to equal this side. The same one, energy has to equal this side because energy in equals energy out. So this is actually increasing the potential energy of it. So I can do mgh, because the h is going to raise up a little bit. Now another way to write mgh is just force of gravity times distance, which is the height of the ramp. So force times distance equals force times distance. You get the same approach. So the same amount of work done is on this side as on this side. The trade-off is this. Here, it has a really, really large distance. It's going to travel a really far distance, which means you don't need much force. Here, it travels a really, really small distance, which means you need a lot of force. But force times distance on both sides is exactly the same. Let's do a couple more. Let's say I'm going sliding down the hill with a friend. I'm going sliding. So I start on top of a hill, and I go sliding down this hill. Here's my angle, 30 degrees. Let's say the height of the hill is 30 meters, which if I do a little bit of math, I can figure out that the hypotenuse of this hill would be 60 meters then. I start on top of this hill, and I sled down. Awesome. Now, if I do this the old-fashioned way, and I want to figure out how fast am I moving when I reach the bottom of the hill, the old-fashioned way of using forces and do that would be this. All right, let's draw a free body diagram, and let's break the force of gravity into vectors. So we have mg sine of the angle going down the ramp. We have reaction force of mg cosine of the angle this way. We have mg cosine angle this way, and we have frictional force acting against us. So then, a net force equation would be this. F net equals ma equals mg sine minus frictional force. Now, if you remember, frictional force is equal to the coefficient of friction times reaction force. I'll write it out that way. Coefficient of friction times reaction force, mg cosine. So we have to get to that part right there, then solve for acceleration. What's our acceleration down the ramp? Then we have to use suvat, where s is 60, u is 0, a is whatever we found here, and v is what we're trying to find out, how fast are we moving. That's a long process. We can answer that same question with conservation of energy. Let's take a look. Using that same diagram here, let's think about what energies it has. So at the very first step, what kind of energy does it have? It has potential energy. Potential energy is mgh. That's what it starts with, is mgh. So I'll start with mgh. That's my total energy to start with. Equals my total energy to end with. What energy does it end with? It ends with kinetic energy, which is 1/2 mv squared. But because there's friction, there's also dissipated energy involved. So I'm going to add on ed. Now the equation for dissipated energy is frictional force times distance. So the frictional force is coefficient of friction times mg cosine of the angle times distance, which is just, in this case, it's 60, the hypotenuse of the hill. So there we have it. Now all I need, that's one step. I would know everything that I knew before, and the only thing I wouldn't know is v. So I can answer the same question in one step versus two. Very cool. Let's do one final example. All right, final example here. So let's say we have Santa Claus and he's sliding down the chimney. Now we want to figure out how fast is he going to be traveling when he reaches the bottom of the chimney. Let's get some numbers here. Let's say his mass is 120 kilograms, and the chimney is going to rub on his shoulders because he's a big dude, and his belly, and it's going to slow him down. So there's a frictional force, an upwards frictional force acting on him of 800 newtons. And the chimney has a height of 5 meters. So I want to figure out how fast is he actually going to be traveling when he reaches the bottom of the chimney. Is it safe for him to actually travel down the chimney? So one way to do it would be the old-fashioned way, net force equation. All right, net force equation, we have F net equals ma equals the upward force of friction, 800, minus the downward force of gravity, which is 120 times 9.1, which is 1,177.2. And I know his mass is 120. I can solve for his acceleration down the chimney. Once I find his acceleration down the chimney, then I have to use suvat to figure out his velocity at the bottom. So it's 2 steps. Well, think about 3 steps. Free body diagram, net force equation, suvat, 3 steps. I can answer that same question in 1 step with energy. Let's think about that. So if I use conservation of energy, let's think about this. If he starts on top of the chimney, he has potential energy, which is mgh. When he gets to the bottom of the chimney, then he has kinetic energy because he's moving, which is 1/2 mv squared. Remember, we set them equal to each other because whatever energy he starts with is the energy he's going to end up with. Now, because there's friction, he also has to use up some of that kinetic energy in the form of dissipated energy. So we're going to tack that on, which dissipated energy is his frictional force times distance. Frictional force times distance. We'll go capital T here. All right, let's look at what we know. Do I know the mass? Yes. Do I know the acceleration of gravity? G. Yes. Do I know the height of the chimney? Yes. Do I know the mass? Yes. Do I know the frictional force? Yes. Do I know the distance he travels? Oh, that's just the height of the chimney. Yes. I know every single thing in this one equation. I can solve for his velocity using conservation of energy. Or I could do the old-fashioned way, figure out all those forces, figure out the acceleration, then use SUGAT to figure out his velocity. You'll get the same answer either way, but energy makes things so much quicker. You can't get all the details of every single problem, but it does simplify a lot of problems using energy. So hopefully, you guys are energized to work really hard and really efficiently through some of these energy problems. Best of luck. Take care.